Swayam Prabha. Digital India. Educated India.
Hello. So welcome to yet another lecture in astrochemistry. This is lecture 8. In the last lecture, we had discussed about the number density, the idea of number density in the interstellar medium versus the idea of number density on Earth. And we found that the number density is much lower in the ISM, as you would expect, because it's after all mostly empty space, right? And how we know the use of commonly utilized equations such as like PV equals nRT, they come with a caveat when we apply them to conditions under astrophysical conditions, such as in the ISM. So this is what we looked into in the last class. Now today, let us look at another extremely cool feature of the ISM. It is that in the ISM, water does not exist in the liquid phase. Now this would come as a surprise for many of you, right? So you would be thinking about it. Okay, gas molecules of water existing, I can understand. Well, if liquid is not existing, then how come solids be existing, right? The question is, I understand that, well, it's empty space, so like lots of water molecules can be floating around, and we understand that at higher temperatures water is only bound to be in the gas phase. Okay, but what about the solid phase then? I did not say that the solid phase does not exist. In fact, it only exists in gas, in the gaseous and solid state. So let us look into why there is no liquid water in the ISM, but then the solid water is possible. Now, how do we address such a question? What is the principle as to what determines whether a substance would be found in the solid, liquid or gas phase? Noticing that we're not talking about one physical condition. We're not talking about room temperature, that is like 300 Kelvin and 1 atmosphere, or something like 273 Kelvin and 1 atmosphere. We're talking about a range of conditions, because in the ISM, it is not a homogeneous medium. It's actually a collection of different regions, as we keep saying, right? So in that condition, how is it feasible? How is it feasible that at all conditions, and not just one condition, water does not exist in the liquid phase, but water exists in gaseous phase in some regions, and in the solid state in some other regions? What is the physical principle based on which we are going to be looking into this? Well, we are going to be looking into the good old thermodynamics. Oftentimes, we read about all these chapters in our chemistry and physics courses, but what is the connection between them to a real applied science? Now, what thermodynamics teaches us is about this idea called as phase diagrams. And what's a phase diagram? A phase diagram is nothing but a plot of P versus T, right? The pressure, the total pressure of any substance versus its temperature, right? A plot of P versus T, which can be experimentally obtained, or in some extreme cases also obtained using some equation of states. Okay, right? So this plot of P versus T is what is called as a phase diagram. And this phase diagram is a very important idea in thermodynamics, which tells us about the state of a substance. Notice that whether anything exists in the solid, liquid or gaseous state, it is not just dependent on the temperature alone, it is also dependent on the pressure. correct? Right? So it is both the pressure and temperature. And when we always talk about, for example, when we always talk about the state of water, we not only mention the temperature, we always mention the pressure also, correct? It is at 1 atmosphere, and 300 Kelvin. That, water exists predominantly in the liquid state. All right. So what determines whether a substance exists in the solid, liquid, or gas state actually depends on both its pressure and temperature. Okay. So both P and T are important. So let us now look into the phase diagram of water itself. So on the x-axis I have pressure. Let's call it in atmosphere, and temperature. Okay, right? And note that 1 atmosphere. Okay, right? 1 atmosphere. Wait, I'll draw this more clearly. One atmosphere is somewhere here. This diagram is not to scale, note. Okay, so 1 atmosphere of pressure is somewhere here. Okay, right? And without knowing anything, without knowing any thermodynamics, right? Knowing that this is 1 atmosphere, right? And let us approximately, put this, let's say we'll have it in degrees Celsius. It can also be had in Kelvin, doesn't make a big difference. And let us say that we call somewhere arbitrarily this point to be 100 degrees Celsius. Okay, right? We call this point as like 100 degrees Celsius on the temperature axis. And this point, okay, this point as like approximately 374 degrees. Okay, right? So just by knowing this much, okay, right, we know that 1 atmosphere. Okay, right? So this is 1 atmosphere. Pardon my drawing of a straight line. Yeah. So at 1 atmosphere and 100 degrees C, in what phase will water be? And less than that, what will water be in? It's going to be in the gas phase, right? Water is going to be in the vapor phase. Therefore, without even knowing anything, without even knowing much about the phase diagram, you understand that this region, this whole region, this corresponds to water existing in the gas phase, correct? Now, if this is gas at 100 degrees, what is going to be the other phase which water is going to be in equilibrium with? It's liquid, right? So you see that this region is going to be the liquid phase. And so in a phase diagram, you get different regions bound by different curves. If this is gas and this is liquid, what should this be? It should be the solid phase, correct? It should be the solid phase. Now, note an important point about the phase diagram. I have clearly not mentioned what the origin is. I'm not going to discuss why it is important, okay, right? And I have not, precisely let this curve touch the origin. There are reasons for it, and I will address them in the tutorials, okay? Because these are fundamental thermodynamic reasons. I will address them in the tutorial. For now, we understand that this is the phase diagram of water, and notice also this line with a negative slope, okay? This follows what is called as the Clausius-Clapeyron equation, and this also we shall discuss in the tutorials. But for now, take this phase diagram for granted, and we have, it's a plot of P versus T, and it tells us what all phases of any substance is possible under different conditions of pressure and temperature. Now, from this diagram, okay, right, from this diagram, it becomes very clear. That, that the gas phase, right, the gas phase of water can of course exist at like very high temperatures, no matter what the pressure is, correct? Beyond, like for example, in this region, we're talking about very high temperatures. It doesn't matter whether the pressure is high or low, because this line is in a different region. All right. So from phase diagram, one can understand that gas phase possible at low pressure as well as high pressure. At low temperature as well as high temperature for a range of pressures, right? Yeah. So I'm talking about this particular region, right? So even at low temperatures also the gas phase can exist, and at high temperatures also, which are the two extrema in the interstellar medium, correct? So therefore, in ISM, gas phase can exist. Next, what about the solid phase? Now the solid phase, until the temperature reaches a certain range, right? Now, by the way, this specific point on the phase diagram, okay, right, is called as the triple point. I'm notifying it with the letter P to emphasize it that this is the triple point. Okay, so in triple point, at triple point, by the name triple, right, all three phases, the solid, liquid and gas phase, they exist in equilibrium. And the triple point for water corresponds to a temperature of roughly approximately, slightly greater than 0 degrees, not exactly 0 degrees, slightly greater than 0 degrees. Let's say, like something like 10 to the power minus 2 Kelvin. I'll write it again, 10 to the power minus 2. Okay, it's not exactly 0, but it's slightly above 0. But the key thing is this pressure right here, okay, right? The pressure right here, it corresponds to approximately 10 to the power minus 3 atmosphere. Okay, right? So the triple point of water, right, is like approximately 10 to the power minus 3 atmosphere and at 10 to the power minus 2 Kelvin. At this temperature and pressure, notice that it is not 1 atmosphere. It is not 1 atmosphere. It is 10 to the power minus 3 atmosphere. At much lower pressures and temperatures, you can have solid, liquid and gas coexisting. Okay, right? What about pressures much below that? And what about pressures above that? At pressures below 10 to the power minus 3 atm, okay, right? Can the liquid phase exist? You just take a look at the diagram. At pressures below this 10 to the power minus 3 atm, can the liquid phase even exist? What's the answer? No, right? Yeah. Clearly, at temperatures below 10 to the power minus 3, liquid phase of water cannot exist. So please make note of this. And now, from our last lecture, what did we see was the pressure range in the interstellar medium? It was of the order of 10 to the power minus 22 atmosphere or something like 10 to the power minus 24 atmosphere. It was so low, right? Which means we're talking about a pressure range much lower, right? So therefore, no matter what the T is, what the temperature is, right? Because the pressure is so low, because the pressure in the interstellar medium is so low, because liquid water is not possible in the interstellar medium. Liquid water does not exist. I'm running short of space. Liquid water not found in ISM. This is the key point. Okay, right? Because the pressure is extremely low. see, 10 to the power minus 3 atmosphere is itself low from our terrestrial standards. However, when the temperature becomes even lesser than that, much further lesser than that, we are talking about at least 2 orders of magnitude, 10 to the, 1 order of magnitude, 10 to the power minus 3, 10 to the power minus 13, 10 to the power minus 23. Okay, it is so low in the atmosphere, in the interstellar medium. So therefore, liquid water is not found. What about the solid phase? So, what about the solid phase? The solid phase can exist for a range of low pressure until you reach a temperature of 10 to the power minus 2 degrees Celsius. Notice that the scale on the x-axis here is Celsius. Okay, right? So solid phase for a range of high pressures right, until 10 to the power minus 2 degrees Celsius, which is what? Which is approximately like slightly, we're talking about like 273 plus some delta Kelvin, right? We're talking about, our delta is a very small number, okay, right? Until this temperature, the solid phase can exist for a wide range of pressure on the vertical axis, correct? Right? So this tells us, but from the last lecture, what did we see was the temperature range in the ISM, especially towards the lower range. It started from around 5 or 10 Kelvin, correct? So this implies that solid phase of water is also feasible in the ISM. So recall where we are at. We are at the point where we discussed about the number density on Earth versus the number density in the ISM. Next, we are discussing about the phenomenon of how liquid water is not present in the ISM, whereas it is present, of course, on Earth. That's why we all live here, right? Yeah. And why is it not present? It is not because of any magic, but it is completely based on fundamental scientific principles. All right. So with this, I have highlighted 2 key distinctions between the interstellar medium and Earth. Now let me address yet another point. Next distinction. Now, let's say I'll tell you that, I won't tell you how yet, that will come in a subsequent part of this course, but I'll tell you that the molecule KCl, okay, so far, right, the first 2 distinctions, the number density part and the existence of liquid water, these were both, principles based on physics and chemistry, that is like thermodynamics, the ideal gas laws, etc., etc. But this is more of chemistry, okay? Why, some molecules behave differently on Earth and in space. Now you take this molecule called as KCl. This has been detected in the ISM. Do we know how? In this course, no. Okay, right? In this course, we do not yet know how. I will address this in the subsequent lectures. Please note this point carefully. So, KCl, do you know whether it is also existing on Earth? We're talking about, like Earth around us. On Earth, not even in the atmosphere. We're talking about on Earth. Of course it exists, right? Yes, it does. Now, forget about the ISM for a moment, okay, right? Now, KCl on Earth. You talk to any good chemistry high school student, or like a chemistry major in college in the first year or so. KCl. In what state does it exist at 1 atmosphere and approximately 300 Kelvin? Do you expect it to exist in the solid state, liquid state, or gaseous state? A priori. It is a prototypical example of what is called as an ionic compound, correct? Because it's an ionic compound, it exists as an ionic solid, right? So in other words, we're not just talking about one K plus and one Cl minus, we're talking about a network of them, a network of them, right? and the stability of the molecule on Earth is due to, I mean, under these conditions, at 1 atmosphere and 300 Kelvin, stability of KCl is due to its ionic lattice. Now, let's go back to, so let us go back to the ISM, right? And I told you that KCl has been detected in the ISM. Didn't tell you which region of the ISM, didn't tell you how, etc. But the KCl which has been detected in ISM, right? Let's assume it has been detected in some molecular cloud where the temperature is approximately 10 Kelvin, and the pressure is very low, of course, right? 10 to the power minus 20-ish, atmosphere. Okay, right? So under this condition, what do you think, in what state does KCl exist? Do you think that KCl can form a lattice, or does it exist as isolated gas phase entities, or is it going to exist in the liquid phase entity? And for this, we're not going to look into the phase diagram itself. Without going to look into the phase diagram, what do you think, a priori, using your intuition, what do you think this is going to be existing in? Well, you would think that, okay, the number density in ISM, is it high or is it low? It's extremely low, right? It's extremely small vis-a-vis Earth, right? So because the number density in the ISM is very small, right? Yeah, KCl can't form a lattice, because from your fundamental high school and probably first year knowledge of chemistry, we know that to form a lattice, how many ions come together? N is a very large number, right? In the formation of this lattice, N is of the order of the Avogadro number, correct? So that is what imparts stability to this ionic compound. All right, yeah. KCl can't form a lattice. Okay. So when KCl cannot form a lattice, what else can it be? Can it be in the liquid state? Well, even to form a liquid, you need sufficient number density, correct? But the number density in the ISM is so low, okay? Or exist in liquid state. Therefore, the KCl detected in space is going to be in the gaseous state. This is what we would expect a priori. Of course, I haven't quantitatively, made an argument here. My arguments are all based on chemical intuition and qualitative aspects. They will, of course, corroborate with quantitative aspects, as we shall see in the subsequent parts of this course. Okay, right? It exists in the gaseous state. But notice a very important distinction about like molecules in the gas state versus molecules in the liquid or in the solid state. Now, molecules in solid state, I'm especially talking about ionic molecules in solid state, the presence of charges, okay, right? We're talking about K plus Cl minus times N, okay, right? The charge stabilized by electrostatic interactions. So the charges are stabilized by electrostatic interactions across the lattice, throughout the lattice. Okay, right? Now, what about ions in solution? For example, you dissociate KCl in water. What happens? The K plus ion is surrounded by the electronegative oxygen of water, and it forms a solvation shell. Similarly, the Cl minus ions is surrounded by the hydrogen part of water, and that also forms a solvation shell around it, right? So ions in solution, the charges are diffused by the solvent. We are typically talking about, like solvents which can actually carry out this stabilization. Typically, we're talking about highly polar solvents. Okay, right? So notice that ionic molecules in solid state and ions in solution are stabilized by different mechanisms. But what about ions in the gas phase? Is there anything to stabilize, any factor to stabilize them? So ions in gas phase, what stabilizes ions in gas phase? Well, we're only talking about very weak attractive van der Waals forces or something like that, right? So there is not much to stabilize the ions in gas phase. So K plus and Cl minus, if they were to be existing as discrete ionic entities, nothing to stabilize them. However, recall that any student who has taken your 11th or 12th standard chemistry knows that no molecule is 100% ionic and no molecule is 100% covalent. You talk about distortion of the orbitals, etc., etc. Let's not delve deep into that aspect. But should KCl exist as a covalent compound of this form, then of course you have like stabilization between the electron nuclear attraction, the orbital overlap, etc., right? There is stabilization. So through this exercise, starting comparing a molecule detected in space, such as for example KCl vis-a-vis how it is found on Earth, right? We understand that a molecule which exists as an ionic solid on Earth, right? It is, when it is actually detected in the interstellar medium, it is in the gas phase. And when in the gas phase, it does not exist as ions, right? It does not exist as ions, but actually there is a significant amount of covalent bonding, almost exclusive covalent bonding. So this is yet another difference between the conditions on Earth and the ISM. The state of the molecule can easily change, right? On Earth, what is the ionic mode of bonding, which is stabilized by the lattice in the solid phase and by diffusion of charges in the solution phase, is however not present in the gas phase. Therefore, in the ISM where we are talking about exceptionally low number density, right? It is not possible to form a lattice, neither possible to form a lattice, nor possible to get stabilized by solvation. Therefore, this is the only way. That is the formation of a covalent bond to stabilize the individual entities. So what is the conclusion from this discourse? It is that are in different bonding state than so molecules in the ISM are in different bonding state with respect to their usual bonding state on Earth. Okay, right? So this discussion I did via a qualitative analysis. Okay, right? However, we can also quantify the same thing. We can quantify the extent of orbital overlap and how much stabilization there is due to orbital overlap in the gas phase, etc., etc. But we're not concerned with that. Now, I will end this class by asking you all a question. What is the common oxidation state of magnesium on Earth? Question. On Earth. Is it +1 or +2? Well, you can give your answer at leisure. I will stop with this. Okay. And with this question, I stop this lecture. And in the next lecture, we shall continue analyzing the various differences between the ISM and the earth. But before that, before we actually go to the next lecture, there will actually be a tutorial wherein, you know, like I will be solving problems based on the lectures held so far. So with that, thank you, and I'll see you in the next class.